Hello and welcome to the second video. Last time I gave you the definition of Katsumori symmetric space as a coset space of the Katsumori group by its so-called maximally compact subgroup, which isn't compact. And now I want to explain to you what is written down here. It says gk.hk equals tau g theta hk, where tau g is defined as g theta of g inverse. And what this does, it defines sort of a multiplication map on the space X. Now why should there be a multiplication map on a symmetric space? After all, well, not after all, but maybe in the beginning, Riemannian symmetric spaces are usually defined as manifolds, Riemannian manifolds, together with a family of so-called geodesic symmetries that are locally defined. In the case of non-compact type symmetric spaces, these geodesic symmetries are globally defined. And what they do, if you apply, well, to every point you have associated this geodesic symmetry, and what it intuitively does is, if you apply the geodesic symmetry associated to the point X to another point Y, it should be thought of as a point reflection. And if they are globally defined, you can really apply, say the geodesic reflection was called sigma x, you can apply for any x, you can apply it to any y, so this sort of works out to define a multiplication, or, well, a multiplication map in the sense that it's just a map from the product x times x to the space x. And this is an approach which is due to Ottmar Loos, and which I call Loos axioms on this slide. And it says a symmetric space is a set X with a multiplication map dot from x times x to x, satisfying a few axioms. Let's quickly go through them. The first axiom is x times x is x. And as I explained, really this dot should be read as reflected. So this line should be read as x reflected at x is x, which is kind of natural, I think. The second axiom is just as natural. It says y reflected at x reflected again at x equals y. The third axiom looks more interesting. You could call it self-distributivity of this multiplication map. It says x dot y dot z equals x dot y in brackets dot x dot z. Or you could say the following way: reflect z at y and reflect this at x, then what you will get is z reflected at x reflected at y reflected at x. And another way to formulate it is that the geodesic symmetry, which is reflecting at x, or at any point x, is an automorphism of this, call it algebraic structure, given by the dot. This, I believe, is a very interesting and natural property. And the fourth axiom is a geometric property. It says if x dot y equals y, so if y reflected at x is still y, so if y is a fixed point of the geodesic symmetry, then x must be equal to y. So this holds only in the non-compact type cases when we're talking about finite dimensional spaces. And there's also a local version of this fourth axiom, which says that this holds only in a neighborhood of u. So for all x there is a neighborhood of x such that inside this neighborhood there are no other fixed points other than x of the geodesic symmetry sigma x, or the geodesic symmetry associated to x. And now this is a really beautiful thing, because these axioms, they work with sets. Yeah, you don't need differential geometry, you don't need topology. Okay, for Kac-Moody groups there actually is a topology, I didn't tell you, but there is one. So you can of course enrich this set of axioms by saying, okay, we have a topology, so also we want this map to be continuous, and we are and yeah, exactly. So this defines a category of objects with the morphisms being, well, maps which respect this dot map. So f of x dot y must be f of x dot f of y in this category of symmetric spaces. And now this formula down here, this multiplication map, is one that satisfies all of the first four properties. Yeah. If you have a Kac-Moody group, the first three, they are obvious from just the fact that you have a group with involution, and for the fourth property there is really something to prove. Okay, I cannot tell you more now. But let's look at some different examples, some more easy examples. Say you take the set R to the n, just real vector space, dimension n, and you define this reflection map x dot y to be 2x minus y. If you think of this geometrically, what this does is really reflecting the point y at the point x. What you do is you draw a straight line between x and y. You drive from y to x, and you drive the same distance over to the other side. And here you have the example. So this first example is the one satisfying all four. The second example is the one satisfying the first three, and the local version of the fourth one, which is a sphere, but it works exactly the same way. It's just a little bit more difficult to write down a formula, but in the picture it makes pretty clear. You have one point y on the sphere and another point x on the sphere. What you do, you connect those 2 points with a geodesic, which is an arc of a great circle. And what you do, you drive to x from y, and the same distance you drive it over to x dot y. And now the third example is less of an example, but it's a very general thing. It just says if you have a coset space G mod K, where K is the fixed point set of any involution on this group, and you define the multiplication map gk.hk to be tau g theta h k, then this will be a space satisfying the first three axioms, not necessarily the fourth. There always something is to prove, but the first three axioms, they are, say, trivially satisfied. Okay, and now this definition of symmetric spaces, it has some more implications that are really nice. Namely, when one talks about symmetric spaces, one always also wants to talk about geodesics and flats. And now this is really easy to define. A geodesic in such a space X is now just an embedding of the real line with this multiplication map 2x minus y, which I just explained, into the space X. Okay, and of course embedding is meant with a respective category that we work in. Maybe we just work with sets, then it's just an injective map. If we have a topology, of course we want this map to be continuous. And a flat in X is just the same thing. It's just you use r to the n with exactly the same formula, 2x minus y. And say a flat is an embedding of such a space, such a flat space into the space X. Now, to arrive at the result that my advisor and I proved, I must first go one step back. I'm afraid it's gonna fly away. I must go one step back and talk about Kac-Moody groups again. And there's a result by Abramenko-Mühlher, which says the following. Let A be a two-spherical generalized Cartan matrix, then G is the co-limit of the diagram D, where D is the diagram which consists of the embeddings of the standard rank 1 subgroups into the standard rank 2 subgroups. Remind the standard rank 1 and 2 subgroups, they are defined to be generated by these exponential images where you pick one I or one J and you have then the exponential of T times at EI and at FI. And rank 2 means you have I and J and you generate the subgroup from these. And two spherical meant that, well, the standard rank 1 and 2 subgroups, they are Lie groups. Okay, so this diagram D is a diagram of Lie groups, and its co-limit, it's not a Lie group anymore, but it's, well, it turns out to be the Kac-Moody group. So this is a result by Abramenko-Mühlher. Which is central to the approach my advisor and I are taking to these groups. Because using this result, you don't really have to think about exponential images of these Lie algebra operators, but you can, well, work just with these small subgroups that are still Lie groups. And just see, from the way they fit together, prove things about them. Okay, let me give one example of how this works. We have the Dünken diagram, which is 3 dots connected to one straight line. Here I wrote the Cartan matrix again, and it's the Dünken diagram or Cartan matrix of the group SL4. Now, the theorem, now here's the diagram D. The theorem said for every rank 1 subgroup, which is for every dot in the diagram, well, we have one group in the diagram, and this rank 1 subgroup is always SL2. So we have 3 SL2s here. So these are the rank 1 subgroups. And now we have 3 pairs of points, namely these ones, and these 2 outer ones. And the 2 connected ones, they give an SL3. These 2 connected ones give also an SL3. And these 2 disconnected ones, they give an SL2 times SL2. And the embeddings of these SL2s into the respective groups, they are just the embeddings as block matrices. So this SL2 embeds as a lower block in this SL3, this as an upper block, and in this SL3, and a lower block in this SL3, and this embeds as an upper block in this SL3, and of course into the product of SL2 times SL2, these embed as 2 factors here. And then the theorem tells you SL4 actually is the co-limit of this diagram in the category of groups. Now, I don't suppose that everybody knows what a colimit is. That's why I wrote it onto this slide. It's a notion from category theory. An object Y in a category C is the colimit of a diagram D, which we specify by the maps Fij from the objects Yi to Yj, if you can find maps, call them iota I, from Yi to Y, such that, now imagine this wasn't there already, such that these triangles, where the upper map is the Fij, the diagram map, and these other arrows, they are the iota maps, so this is iota I and this is iota j, they go to Y. This diagram commutes. And if you have such a thing, it's called a co-cone for this diagram. And co-limit of a diagram is then a universal co-cone, which means if you have another y prime which satisfies this co-cone property, then there will be exactly one map from y to y prime, such that this bigger diagram also commutes. Or to say it more intuitively, you have given some constellation of groups and you look for the object in the category, or now I've said groups, works in really any category, but I've talked about groups. So you have a constellation of groups and you look for the group that contains this constellation of groups within itself. So it's the smallest object containing the certain constellation of subgroups, which is specified by the diagram D. Okay, and now I'm ready to explain the last slide, which is the result by myself and my advisor, Ralf Köhl. And it's very similar to this theorem by Abramenko-Mühlherr. Namely, it says the exact same thing is true, except in the category of symmetric spaces. Not talking about groups anymore. We now let A be a two-spherical Cartan matrix, as it was here, and then what we get is that X is the colimit of the diagram D', which consists of the embeddings of the standard rank 1 subspaces now. Okay, take note, these are then isomorphic to hyperbolic planes into the standard rank 2 subspaces. And now, but now this colimit is not in the category of groups anymore, but really in this category defined by the Law's axioms. Okay, this is everything that I wanted to say. Thank you so much for listening, and we'll see each other in conference things that are about to happen. Thank you.